All right. Next theorem that we have, it is given that En is a sequence. It is a sequence. We have to prove that it is. No. We have to prove that. We have to prove there's the countable union of these countable family is also countable. All right, this is what we have to prove. So we don't know what is E. So first we will try to build or generate E. First we are defining E, that is E equal to union of, that is n equal to 1 to infinity, that is En. Means it does means that En is going from 1 to infinity. For example, like this, E1, E2, sorry for that, E2, E3, so on, like up to infinity it is going on. Now since sorry for the video quality, there is kind of disturbance. Sorry, I am having a focus issue in the phone. All right, I don't know why this is happening to me, but okay, fine. Sorry for that. Okay. Now we are considering sequences, En, sequences of En. All right, sequences of En. For example, we are trying to consider all the sequences that we could generate in En. So there should not be any possible left out sequence. So hence, for example, we are considering first x11, right? For E1, we are considering for E1 x11, x12, x13, so on. All right. Now second E2, we can consider x21, x22, x23, so on, and then we can consider E3 as like this, same as like previous one. All right. Now considering En sequence, that is equal to xn1, xn2, n2, xn3, so on. All right, this is the En, and we're considering the same thing goes on, En plus 1 here, and then this is also continue with that. Now we are saying that these sequences that we have generated, we are saying that this sequences contains all the sequences. So for this, for specifically, we are considering a counter-diagonal argument, where we consider this sequence where the numbers get repeated. Like for example, x11, x11, sorry, x22, x33, x44, xnn, for example, or we can also consider this as well. For example, the order of, or the height of the elements of ith order should be equal. For example, x11, all right, this is the first consider, we are considering the height, and then we have second x21, x12, this is another height. All right, the total will be 3, the total will be 3 here, and then we have considering second third sequence with sorry, one more, sorry, no, not one more, 3 1, this is 3 1, 2 2, 1 3. This is how we have to generate. This is the height with 4. Then we can consider x41, x32, x23, x14, like this. Likewise, we have considered the sequence with the, we are just merging the sequences with the similar heights. Now what we can derive from this is that so what we can derive is from that this all right, wait a minute. Okay, sorry, one more thing that I have left, that is some of the sequences that we have generated over here. In this terms, some of the elements or terms might get repeated, right? So we have to consider that case also. And the sequences which are repeating, we are considering that sequences as we are denoting it with a t, and this t is, we know that it is a terms which is repeating, and they are all positive terms, and we can say that a t is similar to similar e is similar to t. We can say that the one-to-one correspondence will carry out over here, but the given is that t is in the starting question we have t is a subset of j. That is given. It means it has given that e is in the starting. I have considered that e is a sequence of countable set. Countable is a countable family, is also countable, so that is also that is given, so that we have to consider that e is also countable, and that is similar to t. So we can say that t is a subset of j. That implies t might be finite or infinite, but it could be countable, finite or infinite, and or countable. All right, that implies that we know that e1 is a subset of e that we have just now created, and then from that e1 is infinite, we know it is infinite, we know that, right? And then we have t is similar to j, that implies e is also similar to j, we get e is countable. Alright, so this is pretty much the concept of it. Now considering another theorem, that is, if I take the order pairs, for example a cross b. Now if specifically if a is countable and b is also countable, so we are concluding that the ordered pair of a and b, sorry for that, a and b is also countable. That is what we have to prove. All right. First we have to generate the elements of a and b. A can be written in the sequence with distinct terms, a1, a2, a3, an, and it will go down, and b, b1, b2, b3, so on, bn, it goes on. And now now we are creating an order pair set, that is a cross b. We get ak bn, because we don't know the how many number of these AKs are, how many number of BNs are. That's why we are considering AK and N different. K goes from 1 to infinity, and N goes 1 to infinity. Alright, now this is we are naming this set as En for our E's. That's it. And we know that A cross B is a set that is equal to union of these ENs, where N from 1 goes to infinity, that is E1, E2, E3, so on, En goes on. So this is how we have generated the set. Now there will be a one-to-one mapping. If first we define the function that is f maps j to En, where we have to consider f of k equal to ak bn. We are dealing with this part right over here. So whenever we get f of k, the a is equal to ak. All right. Now first we have to consider 1 correspondence. All right, between these functions. Now if considering this, if f of k equal to f of m, we get that ak comma bn equal to am comma bn. There is a function that we have already defined, so we get ak. Whenever we take ak, we get am, so that implies ak is equal to am for some m's, k and m, k is equal to m we get, and since ak's are distinct, they are different. Now we get one-to-one correspondence is over. Now onto, we have to check the condition for onto. Now onto is nothing but all the codomain, domain equal to codomain, domain equal to codomain. You should get domain equal to codomain or domain equal to range, whatever you want to say, you can say. So to prove that f is onto, we should have to prove that there is nothing that is left out. So for that, considering ak, this bn belongs to en. All right, there exists k belongs to j. So again, we get this using the concept of j over here. We have, all right, we have en is similar to j, that is en is countable. Now we have proved all this, ak and bk is countable and infinite. So we can lastly say that the order pairs, that is a and b, a cross b, is countable. All right, so this is pretty much the next theorem that we have considered. Now sorry for that if I do explaining a bit fast, or if I does any mistakes. You can comment me down below if I do any mistakes, so that I can rectify my mistake. And if you like my video, you can comment and share with others, and also please, if you subscribe to my channel, that would be appreciated. Thank you in advance. Now next, let me take the paper. Sorry for that. All right, next term that we are considering is that we are considering the tuples, that is we are considering a is countable. This setup is actually a bit shaky. To be honest, I have to do something for that, but right now I don't have any mean to do that, but I don't have much time for that. But somehow I will try to adjust that in the future. All right, we have is countable set. Then we are considering bn, the set of n tuples, be the set of n tuples. Yeah, we are dealing with matrices. Tuples means the elements of the matrices. That's it, no problem. But we are saying that the element that is getting generated, the elements which are generating this bn, for example, this a1, a2, so on, an, which are generating such that ak belongs to a, that we have considered here, which is countable. This is countable, but we are saying that the elements a1, a2, a3 need not to be distinct. Need not to be distinct, not distinct. Need not to be distinct. And also, even though if it's not distinct, we have to prove that it is the set bn of n tuples is countable. So you have to keep that in mind, that even though if it's not distinct, we can prove that it is countable. In the previous theorem, we have seen that even though the series is getting the elements in a sequence is getting repeated, then at that time also we have considered that the series is countable, even though the series is getting repeated, because we have one-to-one correspondence between E and J. So hence we can conclude that it is countable. So now to prove that theorem, what we have to consider is that first we have to consider that if the series is B, if we are considering the tuple, first tuple, that is one tuple, we can say that one tuple. We are proving this by induction, all right, where we consider n, and then we go from n to the n minus 1. So if it is true for n, then we get that it will be true for n minus 1, n minus 2, so on. All right, this is the induction. It pretty much induction says us. But if we consider b1, there is n equal to 1 here right now. So b1, we get ak. AK belongs to a. K is considered to be 1 here. So we are using only one tuple. So in this case, we get b1 equal to a is countable. Since a is countable, we get the 1-1 mapping between this. Now, if I consider b, if I consider bn, I don't know right now what we are considering for n for what, but b comma a maps b belongs to b n minus 1, so the a belongs to a. This is how we define a set. Bn is a sequence, means it is not fixed. That is, we are considering for generalizing, we are generalizing this n. Now generalizing means we are we are making it fixed b, we are making b fixed, and we are using this a which is getting changed. All right, a belongs to a, and it is we are going to get a set similar, a set like this, set like this. For example, b a1, b a2, all right, b a3, so on, b a3, b ak. All right, this is how we have constructed a set, and then we can write this bn as the union of fb's, because we are naming this set as fb for our ease. Now we have bn equal to union of fb's. Now we are just defining a mapping from fb to a, because if we prove that it is 1-1 correspondence to a, then we can pretty much say that it is a countable set. fb is a countable set. Countable set. fb is a countable set, and hence we can conclude that bn is also countable. All right, now first we are defining 1-1 correspondence for that. For example, if I am considering this every map function, we are considering the function that is f comma a b equal to a. That is what we did right previously. B is fixed, a is getting changed, so we have fb a1 and fb a2. Now from this we get that a1 equal to a2, we get that b of a1 equal to b of a2. We get 1-1 correspondence. Since it is 1-1 function, we can prove for onto as well. For onto, we just have to prove that fb, the set fb is similar to j. That's it. So b comma a belongs to fb, we know that, right? So f of b comma a equal to a, we just have to prove that. So therefore we get that fb is similar to j, because for every b of a, a1, a2, a3, we are getting this a equal to a. So this every set in this fb is getting mapped to another element. So from that we can say that codomain range domain equal to codomain. All right, so from this we can imply that fb is countable. All right, since it is mapping to a which is given that it is countable, given it is countable. So when we get the similar equivalence relation with a fb is equivalent relation with a, we get that fb is also countable. All right, now next story for the papers and this lighting condition, my voice, everything is a bit complicated right now for me to set up all these things. I don't, inshallah, I will try to rectify the mistake. All right, we can cut this out, to be honest. Okay, now this next theorem that we are dealing with is the set of all rational numbers. This q is countable. We have to prove q is countable. So previously we have seen that, for an example, we have seen that z is countable. All right, and we know that q can be written as p by q. The set of rational numbers is written as p by q, where p belongs to z and q belongs to z naught. That is, z naught is nothing but numbers excluding the numbers which does not include 0. So here z naught means it will not be equal to it will be equal to set of all integers, set of all integers excluding 0. That's it, nothing else. So we've got p equal to z because we, and q also equal to z naught. So from this we can say that it is 1 correspondence to integer, set of integers which is countable and infinite set or infinite set. And here z naught is a countable infinite subset of z naught, right? Subset, you can say that subset, right? So first we have to define the function for that is on z cross z naught. All right, we are defining a function z cross z naught that is f maps q to z cross z naught. Means we have to prove that this rational number is 1 and onto correspondence. We have to check that if we can get the 1 and onto correspondence to q to z x to z naught, z x z naught. So first we have the function f p by q. This is the form of rational number. We should get at least p comma q, that is some elements which belongs to z cross z naught, z x z naught. All right, p q belongs to this. All right, now first we have to prove f is 1 all right. For that we have f p by q equal to f r by s. All right, from this we can write p comma q is equal to r comma s. From this we can write p comma r equal to q comma s. We get that q is equivalent to a subset S of zx z naught. We get that q is a subset of this. If and one more thing that we have to include here is that this S is infinite. All right, since q is infinite. All right, and S is countable. All right, f is countable because we know that if s is countable, because we can have, because S is a subset of infinite subset, and this Q is countable, so hence we get that infinite subset of a countable set S, countable set of a Q, that is S, is also countable. We get the one-to-one, and we get this one-to correspondence with J, and hence we can conclude that Q is also similar to J. Hence we get that it is also countable. Q is also countable. The next concept that we have here is that all right, now we are considering a theorem which is related to uncountable sets theorem, where we have to prove that set A of all sequences with digits, with only digits 0 and 1 is uncountable. We have to prove that, right? A is a sequence like 1 0 0 1 0 1 1 1 goes on. This is a sequence we have got. Now the same thing that we have to do over here is that we have to construct a sequence of A, a subsequence of A, that is we are naming it as E. E is a subset of A. We are considering this E, and we are considering that E is countable. We are thinking that we are presuming that E is countable. When we get that E is countable, we know that infinite subset of set, if countable, then the set itself will also be countable. So for that we are considering E is countable, and E can be written as a sequence of S1, S2, S3, so on. We are including all the sequences here. Now if we are getting the sequences, that is the nth digit of S, each sequence will have nth digit, right, of its own, nth digit, all right, of its own. If we are saying that if S1, if we get that 1, we have to select 0. If we get 2, if we get 0, sorry, we have to select 1 for the sequence. Now by this we are considering S1, S2, S3, S3, and so on. Since each and every sequence that we are constructing will be different from the previous sequence, so we can say that S does not belong to E, sorry, because we know that what we have presumed that E is countable, right? But we are getting that S is not countable because we are getting different sequences for each and every sequence, because we are considering 1 or 0. Either 1 or 0 will suffice the parts of a sequence and will change the sequence accordingly. So from this we can get that if E is not countable, if the subset which is a subset of A, hence we can conclude that A is also not countable. This is very much a simple theorem. Now we have next, that is if we consider 0, 1, it is an interval, which is a set which is uncountable. So we have to prove that this set is uncountable. All right, so to prove that it is uncountable, what we have to do is that we have to think that we can prove this set 0, this interval interval 0, 1 as a we can assume, or we think that this interval can be generated by the sequences that we used previously, all the sequences that we could generate. For example, S1, S2, so on, are the sequences between 0 and 1. All right, since the numbers between 0 and 1 are infinite, we get that sequence that we are getting will be equal to infinite sequences. And now if I consider this sequence S1 equal to 0.u11, u12, u13, so on. All right, S2 equal to 0.u21, u22, u23, means it's a decimal expansion, means we are considering the sequence which is between 0 and 1, so you will get the numbers between 0 and 1 in a decimal expansion, right? So we get Sn that is equal to 0.un1, un2, so on. All right, unn, it will go on. So we are believing that this sequence, that the sequences that we have generated, will consist of all the numbers between 0 and 1. There is no number which is not present in this sequence. So we are believing that we have got every number between 0 and 1. So this is the pretty much concept of generating these sequences. All right, now for this, what we have to consider is that if, for example, let's see what we can do with it. For example, if I have a set that is a number, not set, a number that is equal to 0.u1, u2, u3, go on, where n equal to 1, 2, 3, so on. It will going from 1 to n. Now we are saying that we have to put 1 if u and n equal to 0. This is, for example, unn, we get unn, then you have to put 0. For example, unn, we have to put 0. All right, if 0, 0, if we don't get unn now equal to 0. All right, so this is how we are considering generating another number. If you observe that this y will be different from each and every sequence that we have generated previously. So by this we can conclude that this interval 0, 1 is an infinite sequence, and it is uncountable. So this is one more example for uncountable set. Because this y will be different from all other sequences, right? But previously we believed that this sequence that we are generating here will consist of all the numbers, but our assumption gets contradicted when we consider this set. This set is pretty much different or does not belong to the sequences Sn's. All right, so every decimal place will get changed whenever we are considering this. All right, now we have, sorry for that, but I'm going pretty much fast, I believe, but if you can able to understand, then that's great. Or maybe I might be explaining a bit slowly. You might be getting bored, but my aim is to speak or explain as much as concepts as I can in this specific video, so that you don't have to search on internet for each and every concept or topic. All right, so we can say that real numbers, the real numbers also uncountable. All right, we can get also real number also countable, because the series, the interval 0 comma 1 belongs to real numbers, and we have already proved that 0 comma 1, this interval, which is a subset of R. So if this is uncountable, then we can conclude that it is also uncountable. All right, so this is also pretty much simple. Now one more thing that we have to consider is that if E is a set, all right, E is a set, and another theorem, actually it's another theorem, if E is a set, all right, and there is a finite subset, there is F, E is countable set and F is a finite subset of E, then what we are saying that E minus F, if we are just removing this out, E minus F, that is E minus F, sorry for that, E minus F, what we have to prove, E minus F is also countable. Given that E is countable, all right, we have to prove that E minus F is also countable. This is simple, right? From the example itself you can get it, but you can write, think about it. All right, E is countable and F is also countable. One more thing, that E is finite, then F also should be finite, right? Now we are considering that E equal to, we can write E equal to E minus F union F. All right, here we have E minus F, here we have E minus F union F. All right, we have considered two things, that is, given that E is countable, right, is countable, that implies these two sets also countable. So previously we have proved that countable union of countable sets is also countable, so we get that E minus F is also countable, right? And one more thing that we can do with it is that we have E is countable, right? Countable, and F is finite, all right, and F is a subset of countable set E, all right, so we can write countable, we can write E union F also countable. Sorry for that. All right, now one more thing that we have here is that if we have E which is uncountable, all right, F a subset of E finite, we have to prove that E minus F is uncountable, all right, E minus F is uncountable. So we are proving it conversely, that if E minus F is countable, if E minus F is countable, then that means we can get E minus F union F equal to E also countable, alright. But previously we have seen that but in question that it has given that E is uncountable, so that contradicts what has given. Hence we can say E minus F is uncountable. All right, now this is pretty much about the concept of countable and uncountable sets and related theorems. Hope I have explained you people clearly. If you have any doubts in that, you can comment down below or ping me. Thank you very much for watching my video. If you like it, please subscribe.